Hello everyone. Today we are going to cover the remaining parts of general organic chemistry. We already solved so many concepts of basics of organic chemistry, starting from the carbon and the types and the reactions. In the first part, I'll be giving the link in the description. You can watch that. In today's video, we are going to cover the reaction intermediates and the electronic effects in organic compounds, and depend on that how the acidity and basicity varies in organic compounds. Okay, so without any further delay, let's get started. So first of all, if a reaction happens, if a reactant is reacting to give products, so will that give the product in the initial stage, or will undergo a series of reaction to give the final end product? Of course, it will undergo the certain stages, it will jump the threshold, and it will form the intermediates to give the product, desired end product, right? So those are called intermediates. So after forming intermediate only, the reactant give our end product. Intermediate or the short-lived species, then the reactant and product. This can be of many types. So in an organic reaction, the reaction will always proceed preferably in a direction where the stable intermediate can be formed. Okay, so intermediate must be longer lived when compared to the other intermediate formation. What is that, ma'am? What are you referring to intermediate? I'll tell you an example. For example, if I am taking CH3, CH double bond CH2 reacting with HCl. Okay, so what are the intermediates it can form? First, it can undergo slow step, which is the rate determining step, to give an intermediate like this. So the double bond breakage will happen and CH bond CH2 and H plus will get joined to this carbon. This can be one of those intermediate, which is a secondary carbocation. What about another intermediate formation? In this case, H plus will join on the secondary carbon, CH3, CH and CH2 plus. Here the carbocation is primary. So tell me, which is more stable carbocation, primary or secondary? Of course, secondary carbocation is more stable compared to primary. Why is it so? We are going to cover that in today's session. Okay, after that what will happen? After that the Cl minus will get attached to the most stable intermediate to give the product as CH3, CHCl, CH3. So that would be our major product, which is 2-chloropropane. If the reaction goes via less stable intermediate formation, then the product is CH3, CH2, CH2, Cl, which is 1-chloropropane. That is a minor product. So hope you got an idea what is intermediate. So how the intermediate affect the product formation. Okay, so is there any types of intermediate? Yes, it has some types. Before that, I would like to introduce how the reaction happens, how the bond fission happens. Like in the first example, I showed you the double bond is breaking. And the HCl, the bond between hydrogen and chlorine, which is also getting separated. So the bond breaking will happen over there. How that happens? What are the types of bond fission? Fission means separation, right? So what are the types of bond fission? It can be of homolytic fission and heterolytic fission. As I told you, homo means same, hetero means different. So first let's talk about homolytic fission. Homo, which is same. Lytic means separation. So if I am having a molecule of A2, that can be referred as A bond A. So in case of homolytic fission, the bond, the A of A placed in the corners of the bond will get one electron each. For example, the one electron will go to one A and another electron in the bond goes to another A. So as a result, 2A is having one electron each out of the separation. Okay, so this is called homolytic fission. And what is this intermediate is called? This intermediate is called free radical, where it has unpaired electron. Okay, so this is having only one electron, which refers to as chargeless, and since it is having one electron, that is a paramagnetic species. Also called as odd electron species. Any example we encountered in our reactions? Yes. I'll give you an example of Cl2, which can be written as Cl bond Cl. Each one of those electrons will be taken by Cl. So you have to remember one thing, only one electron is going to one atom. So I have to refer this as this kind of arrow. It's not a double-headed one, it should be a fish hook arrow. This is called fish hook arrow. Okay, so as a result of this, I will be getting 2 Cl radical. Mostly the reaction happens in the presence of sunlight or UV will happen like the radical formation, free radical formation. Okay, one more example I will give you for carbon free radical. That is, if a carbon is breaking like this, I am having a Cl radical. So if the breaking happens like this, then it will lead to the formation of carbon free radical plus HCl. Because each one of those hydrogen free radical and Cl free radical is combined to form HCl. Okay, so this is carbon free radical. Okay, so these species which the carbon is having an odd electron, please remember, and this is paramagnetic, that is not having any charges. What about the hybridization of these compounds? What about the hybridization of this carbon free radical? As you can see here, that will have 7 electrons total, right? Already carbon is having 6, the 1 electron from the bond, so it will be a 7 electron. So which will be look like carbon Let's say these bonds are filled with the substituent. You can take any substituent or hydrogen also. Remaining one electron will occupy one of those orbitals. Okay, so in this case, what would be the hybridization? So the hybridization of this carbon will be sp3 but trigonal pyramidal shape. Okay, so you can take CF3, you can take CH3 radical. And one more thing you have to remember, these are electron deficient compound. These are electron deficient compound because that lacks of one electron. Okay, so what about the intermediate stability? Which intermediate would be more stable? If I am comparing it with CH3 or of all three sides and one radical, and if I am comparing it with secondary carbon, and if I am having primary carbon, out of these three, which is more stable? Of course, the tertiary one is more stable when we are compared to secondary, and then comes primary. Why is it so? We'll see in a while. You will understand in a while automatically. Okay, the next type of cleavage or fission, which is heterolytic fission. So heterolytic fission means it's not same, it's different, is it? So if I'm taking A, B, that is giving A plus and B minus. So what it indicates, both the electrons are taken by B and A becomes positively charged, which lacks of electron, which lacks of negative charge, right? So heterolytic fission leads to the formation of ions. For example, you can take C with Cl, okay, which will give you carbocation and Cl minus. So the electron will get shifted to Cl. Okay, so these are called carbocation. Cation means positively charged, we know. Here the carbon is positively charged, so this is carbocation. Okay, so what is the property of these carbocations? Of course, these are positively charged species. These are one of those intermediates. Positively charged. And what about the hybridization? This is sp2 trigonal planar. So where it is having an empty p orbital, right? And most importantly, these are electrophiles. Ma'am, what is electrophile? These are electron deficient or electron loving species. Which will be ready to accept the electrons. Any other examples you see in a normal reaction? Here you can see BF3, which is also having a trigonal planar structure and that is having a empty orbital in it. Similarly, you can try it out with AlCl3 or you can try it out with C+. Correct. So these are some Lewis acids you can take which is ready to accept the electrons. These are some electrophiles example and which are electron deficient also. Okay. Then let's move on to magnetic property, whether that is paramagnetic or diamagnetic. Of course, that is a diamagnetic species because there is no unpaired electrons like we saw in free radicals. These are diamagnetic. And what about the minus charged species or negatively charged species? How it can be formed? And you said carbon will get positive charge and Cl will get negative charge. Carbon can also be negative. Yes, it can. For example, here if I am taking with MgX, where Mg will be more positive, that is a metal. So it creates C minus plus Mgx bearing a positive charge. Okay, so this is called carboanion. Okay, let's list down the properties of carboanion. Negatively charged, whether it will be paramagnetic or diamagnetic. It's diamagnetic, of course. It is not having any unpaired electrons, and this is an electron rich substance or electron rich species, which is also called as nucleophiles. It's just opposite to electrophile, which are hating electrons. Any other examples for carboanions? Yes, we have. It can be of any species which are bearing minus charge. Here you can see carbon is having minus charge, that is a tertiary carbon. Similarly, you can write down for secondary carbon and primary carbons as well, and methyl as well, methyl carboanion. More importantly, you will see this type of structure, CH2 double bond CH, CH2 minus, which is called as allylic carbocation. Carboanion. Allylic carbon is the double bond, the next to double bond bearing carbon. So what about the carbon which is having the double bond? For example, like this. Then that is vinylic carboanion. This is vinylic carbon. And you have to understand one more, that is benzylic carbon. For example, the carbon attached with the benzene ring. You should not take this carbon as a negatively charged while reacting with this kind of benzylic carbon. You please be careful. This is benzylic carbon, the carbon attached with the benzene ring, not in the carbon in the benzene ring. Okay, so these are the only intermediates? No, there is one more, that is carbenes. What is that? So carbenes are the one For example, if I am taking a structure like this, I am treating it with alcoholic KOH, let's say KH plus and OH minus. So what will happen? Obviously H plus will be created by donating all those electrons to carbon, right? Similarly, chlorine will take up both the electrons from the bond and leaving those bonds. So this will create a empty space, empty orbital over here, and this will create a 2 carbon over there on the carbon, 2 electrons on the carbon. Remaining the product or KCl and H2O will be formed. Okay. This kind of carbon is called carbenes. Okay. Where those electrons will reside? We have 2 electrons in the carbon. So where that will be occupied? So carbenes which are bearing 2 electrons, lone pair electrons, that can be of 2 types. One is singlet carbene, where the electrons are in the same orbital. This is empty orbital produced in the above reaction, and both the electrons are in the same orbital, that is called singlet carbene. And if an electron is on the different orbital, then that is triplet. Then that is triplet carbene. Okay. So how the name comes, it's not so important over here. That is depend on the s prime multiplicity. But you can remember this is if both the electrons are in the same orbital, then that is singlet. Both the electrons are the different orbitals. You can remember that as a triplet. Okay, so out of these two, which is more stable, singlet or triplet? So for that we have to understand their properties. The first one, singlet, which will have sp2 hybridization. In case of triplet, it will have sp hybridization and linear. So if sp2 means that will be bent structure like water. This is linear, and you know about magnetic property. The singlet one or diamagnetic, and the triplet one is paramagnetic. Okay, so among these two, which is more stable? While talking about the stability of singlet and triplet, you can clearly see that in case of singlet, that will experience more of repulsions, electron-electron repulsion, which makes it less stable than the triplet one, which is not facing any issues. Okay, but there is one exceptional cases where it comes the formation of back bonding. What is that back bonding? We know that singlet will have an empty orbital in it, like this, which will have an empty orbital. So what will happen if one of those places, if I am having Cl, if I am having any electron-rich species which will be able to donate its lone pair. So in that case, this can accept that electrons, this empty orbital can accept this electron to form back bonding. So if more bonding means what will happen? More strong. It will have more stability. That kind of stability will not happen in case of triplet, even that is having Cl, so which makes it more stable for singlet due to back bonding. If there is a back bonding possibility, then singlet is more stable than the triplet. So back bonding is nothing but p pi bonding. Okay, so now it's time to focus on more of displacement effects. So if you heard this much, take a break for 5 minutes and come back with full potential. Let's focus more on electronic displacement effects. What is that? Why that is so important to understand this in covalent bonding? Because this determines the stability, because whatever the reactions happening in the world, its final destination, final place, why that is happening, the reason is that stability. So these 4 effects, the first one is inductive effect, second one mesomeric effect, or also called resonance effect, third one, that is hyperconjucation, also known as Baker-Norton effect, and the fourth one, that is electromeric effect. We have to understand these 4 to know their stabilities of carbocation, carboanion, free radicals, carbenes, and etc. Okay, now let's start with the inductive effect. What is that? So inductive effect is nothing but it is a permanent effect. What happens over here? Permanent displacement of sigma electrons, that is more important. Sigma electrons along the, of course, the saturated carbon chain towards more electronegative atom. Of course, it will go to more electronegative atom, because electronegative means which directly refers to the attraction of electrons towards itself. You can see in the carbocation formation, in the particularly the heterolytic cleavage, heterolytic fission, where if there is more of electron negativity difference, then it will undergo heterolytic fission. If the electronegativity is less or same, for example Cl2, that will undergo homolytic fission. If I am taking HCl, that will have more electronegativity changes, differences. So it will undergo heterolytic fission, right? So here we are talking about permanent displacement of sigma electron towards the electronegative atom. What is that? Let me take a carbon which is attached with the electronegative atom, that is halogen, let's say. So what will happen? This is having a more electrons, electronegativity, so which will pull the carbon electrons also, because this is electronegative. Due to that, The negative charge, slightly more negative charge is produced on this electronegative atom due to pulling of electrons and giving up of electrons. It's not entirely giving up, but the electrons are moving towards halogens or any electronegative atom, so that here slight positive charge is produced. Okay, so which will lead to the polar covalent bond. Which will lead to polar covalent bond. What is polarity? Difference in charges, is it? So which will lead to polar covalent bond. Due to the more electronegativity of an atom, it is just pulling those electrons. Due to that, the slight positive and negative charges created on the respective atom. That is called inductive effect. Okay, so this is having two types: positive inductive effect and negative inductive effect. So where positive inductive effect happens? This happens where the electron releasing groups are there. Electron releasing groups are also called as electron repelling group. You can take anything. For example, all alkyl groups, which always wanted to be in positive charged, so which will give up, which will ready to give up the electrons. So all alkyl groups are undergoing plus I effect. You know, I told you why tertiary carbocation is more stable than the secondary, then comes primary and then methyl. Because tertiary is having more positive inductive effect. It's just giving up the electrons to positively charged carbon to neutralize the compound, so that will be more stable. And if I'm comparing it with secondary, what will happen? That is having only two methyl groups. And for primary, that will have only one methyl group. So that's why tertiary is more stable than the secondary, then comes primary. Is it clear? This is super important. Whenever you are doing any reactions, this is much more important. Okay, so what about minus inductive effect, minus I effect? That's just opposite to plus. Where will happen? Electron withdrawing groups are there, means electron withdrawing groups. For example, halogens. Any group or an atom which is having more electron attracting power than the hydrogen, there this effect can have. More electron withdrawing than hydrogen, this effect will happen. You can take halogens, you can take nitro, cyano, even alkynes, alkenes. Okay, so these will undergo minus I effect. I can give you the order also. For example, nitro, which will give you more electron withdrawing effect, and then comes cyano, then keto group, then comes our halogens F, Cl, Br, iodine, OH, don't get confused with other effects. In case of plus interactive effect, only alkyl groups. Remember it like that. Only alkyl groups. In case of minus I effect, you can take these groups. Mostly your exams will get covered with these groups. Okay, ma'am, why are you dragging these alkynes and alkanes over here? Of course, these are also having more electronegativity, because this is sp hybridized with 50% s character, and this is sp2 hybridized, where it is having 33.3% of s character. More the s character, more will be electronegativity and more acidity, isn't it? Okay, are we clear about minus I effect? So, why we need to understand minus I effect? What is the application of minus I effect? I'll give you shortly. The first thing, stability of carbocation. I told you. It's depend on plus I effect. Okay. Then the second application is stability of carboanions. Carboanions which is negatively charged. So negatively charged, if that is having electron withdrawing, means that will get neutralized, so that becomes more stable than the electron releasing group presence, right? For example, if I am taking CH2 minus with this attached with NO2, okay, that becomes much more stable because NO2 is taking up the electron, trying to take up the electron, so that the negative charge become balanced, so which becomes more stable. Then comes methyl, and then comes if an electron releasing group is attached, like for example CH3 CH2 minus. So in that case, already that is electron rich, negative charge is having, this is also giving the electron, means the stability will get decreased. Okay, but here you have to consider one thing. If I am taking CF3 minus and CCl3 minus, then CH3 minus. Okay, so what will happen? We discussed it earlier. In this case, this guy is having negative charge and 3 fluorines attached to it, fluorides, so which will take up the electrons. Okay, what about CCl3? Once again it will have and CCl3, it will try to take up the electrons. In that case, what can happen? Cl, particularly Cl, is having a empty 3d orbital. Empty 3d orbital, isn't it? So Cl configuration, which will have empty 3d orbital, so that these electrons will form a bond which is called p pi d pi bond. Which makes it much more stable. Then in case of CH3, we very well know about that. There is nothing to talk much about CH3 carboanion. So, which is more stable? What would be the stability order? If I am talking about the stability, CCl3 is more stable than other two. And then comes CF3 and then CH3. Okay. Then the third application is basic strength of amines. So amines which will have NH2 groups. Amines that is having a lone pair in it, the nitrogen. So this is also called as Lewis base, which is also called as nitrogen is willing to donate the electrons. So if the ease of donation increases, then what will happen? The basic strength will increase. So comparing primary, secondary and tertiary amines becomes more basic, then comes secondary, then comes primary, then ammonia. Because already nitrogen is willing to donate, CH3 groups, alkyl groups attached to the nitrogen will make it much more easier. So increase of ease of donation means increase in basicity. Okay, so the next application, that is acidic strength of carboxylic acid. So carboxylic acid that will have COOH group. As the name indicates, that is more acidic. So what will happen to carboxylic acid? Because of this inductive effect, OH is there. So which will form the conjugate base of C double bond O, O minus, right? Because H plus will be leaving, so O is more electron withdrawing, more electronegative. It is forming a conjugate base. So the conjugate base is more stable, the acidity is increases. Conjugate base stability is directly proportional to acidity. Right. So the next effect we are going to talk about is resonance or mesomeric effect. This is very simple effect and a very important effect to be remembered. It is resonance effect. Where we heard about the term resonance? While we are talking about aromaticity, benzenes, we talked about it, right? So which is nothing but delocalization of pi electrons. Delocalization of pi electrons in conjugated systems. Conjugation means alternate double bonds, double and single bonds, right? So in delocalization of pi electrons in conjugated system is called mesomeric effect. For example, you can take how the delocalization happens. So the first double bond will give up the electrons to the next carbon. So this becomes positive. I'm writing it here. So this becomes positive and CH that becomes negative. Then comes Then this negative, which is combined with the positive created by this carbon, so which forms the bond, then you have to proceed with CH2 with the positive charge. So here there is no negative which involved in the bond formation. Okay, I could delete it. Please forget this. So this is what the delocalization happens. So what is the importance of this? So remember one thing. If you are having more weight on your hand, how many hours will you able to sustain with that weight? Let's say 2 hours. If you are having your friend beside you and you are changing the hands of your weight, how many hours you can sustain with you two with the weight? More than 2 hours, right? The similar thing happens over here. The delocalization increases the stability. This is also categorized as plus M effect and minus M effect. Plus M effect groups are where it can happen is wherever the electron donating groups are there. Electron donating means electron releasing. Wherever the electron donating groups are there. For example, OR, OH. Ma'am, you told OH is in minus I effect. Yes, I do. That's why I told you don't get confused. OH, which is having a oxygen that is negatively charged, electronegative, that's why it is giving you the minus I effect. Here we are talking about electron donating groups. So where NH2 comes and NHR, where it is having the lone pairs. Here also oxygen is having the lone pair which can donate. And what else? Halogens, of course. So the halogens which can donate the electrons. Here what can happen? For example, if I am taking CH2 double bond CHCl. So Cl is having a lone pair which will be given up to the bond formation. So can form CH double bond Cl with the positive charge, and what happens to this carbon, the first carbon, that becomes negative with a single bond. Okay, so this kind of delocalization can happen. You can consider the best delocalization example with the benzenes. Okay, so here the question can be asked, compare the bond strength. You can consider CH3, CH2Cl and CH2 double bond CHCl. Comparing A and B, which is having more bond strength in case of CCl? Which is having more bond strength in case of CCl? A or B? So let me know in the comments below, A or B. If you don't know the answer also, let me know. We'll discuss it in shorts. Okay. I told you with this the best example in case of benzene. That's it. So let me take this phenol. Okay. So what can happen? Oxygen is having the lone pair. So it is donating to this carbon. So the positive charge negative charge goes over here. The bond is taking up the positive part. So which creates a negative charge on this carbon and double bond over here, and oxygen becomes positive. Remaining bonds remain same. Then again this negative charge goes here, so that this position, para position, becomes negatively charged. Guys, this is very important. You can see this delocalization in hydrocarbons chapter as well, where how the electrophile directing happens in case of substituent presence, right? So please be careful, please be mindful while you are drawing this. So the negative charge produced over here, the double bond comes here, oxygen with the positive charge. Then once again double bond, double bond, double bond O with the positive with hydrogen, and a negative charge go to another ortho position, which makes it again the benzene structure with varying double and single bonds, right? So here you can see ortho and para positions are electron rich. So you can say if electron releasing group is present over there, means ortho and para positions becomes electron rich, which triggers the electrophile to come and attack over there. Okay, so what about minus I effect, ma'am? Minus M effect, ma'am? It's just opposite to that. Electron withdrawing groups are present. For example, nitro, CO, cyanide, and much more. I will be attaching the list of electron withdrawing and electron donating groups over there. You can draw a benzene structure with an electron withdrawing group, that is, let's say nitro. So where it has the nitrogen that is having a, either you can mention it in the coordinate bond, I'm just mentioning it with charge. So it is taking up the electron. Due to that, what will happen? This part becomes positive, right? It is taking up the electron, so this part becomes positive. So double bond, oxygen with the negative charge, and remaining stays same. Again, you can consider, again it will pull up the electrons, so the double bond will be placed over here and the positive charge goes to para position. Once again the resonance happens, another ortho position becomes negative, and finally it becomes positive, and here comes the double bond O. Again nitrobenzene is formed. You can see, comparing ortho, para and meta positions, meta is electron rich. If electron withdrawing group is present in the benzene ring, and ortho and para becomes electron deficient. Okay, this is point to be noted, please note it down. This will be very helpful in case of substitution reactions. We already discussed about the stability, which will give you more stability, more the resonance, more stability. And in case of carboanions, plus M effect decreases the stability, and if there is a minus M effect, it increases the stability. And resonance in phenol, we already discussed about that, and how the electron rich and electron deficient positions are created. The next effect we are going to talk, that is hyperconjugation. So hyperconjugation, this delocalization of, sorry for this spelling mistake, it's delocalization of sigma electrons again, sigma electrons, which is also called as no bond resonance. There is no bond, yes, there is no bond formation. It's like bond will disappear. Like for example, you can see the first type, that is sigma to PMT, where it happens like if I'm taking CH3 attached with an carbocation, that will have a empty orbital, is it? So that empty orbital, that is a sp2 hybridized carbon, the electron shift happens to, this is sp2 carbon. Okay, so the bond breaking happens over here. H plus is going or sitting there like this, and due to that what will happen, it will become electron rich. So those electrons are given to this empty orbital, so that the double bond will be formed. So which makes this more stabilized. That is happens for each of these, any of these hydrogen can go, right? So how many hyperconjugative structures can be written for this? There are 3 hyperconjugative structures for each one of these hydrogens. So total 3 hyperconjugative structures. So why the hyperconjugative structures are important? How we can determine how many hyperconjugative structures can be written? So the number of beta hydrogens is equal to or proportional to, you can take the hyperconjugative structures. More the number of hyperconjugative structure, more will be stability. Okay, so for example, if I am talking about tertiary, that will have tertiary carbocation, then that will have 9 beta hydrogens, correct? So which will have more stable. Then secondary, which that is having 6 beta hydrogens, and then comes primary, that is having 3 beta hydrogens. Then finally methyl carbocation, that is not at all having any hydrogens, so which makes it least stable. The most stable one is tertiary carbocation with high number of hyperconjugative structures. Okay, so let's move on to alkenes. So what happens to alkenes in case of hyperconjugation? Here you can see, let me take CH3 in one of those substituent. So what will happen? This hydrogen will goes away, the carbon gets the negative charge, so that negative charge will get shifted to this carbon, correct? So due to that, what can happen? The shift, so that the formation will be C with H plus, other two hydrogens will be there, then double bond will be formed in this carbon and the single bond will be there in this with the negative charge. Similarly, you can form the structures with other two hydrogens as well. So if you are having CH3 in all four positions, then you can have more number of hyperconjugative structures. Okay, it's more related to the resonance, but it happens in case of sigma electrons, but the resonance happens in pi electrons. Okay, in the last effect we are going to see, that is a very simplest effect known as electromeric effect. Among these four, this effect is very simple effect. Also, this is called temporary displacement. Why this is temporary? Because it is dependent on the incoming group. For example, if I am having the alkene system, okay, so I am having alkene system, the incoming group is Cn minus, let's consider. So the Cn minus makes it, it will break the double bond. Let's say H plus and Cn minus. So H plus will get attached to the one of those carbons and Cn minus will get attached to the another carbon, right? So due to the H plus presence, so what will happen? The attraction between one carbon to the H plus, correct? So in that case, bond breakage will happen. So this becomes slightly positive, negative, and this becomes slightly positive. So the bond breakage, here comes C with the H plus attached to the CH, and this carbon becomes positive, and followed by Cn attack, so that Cn and HCN will get attached. So what if instead of H plus, this Cn is starting over the reaction? Then one of those carbons will get negative charge. So that's carbocation formation, carboanion formation, that discussed about the electromeric effect. Okay, so in today's session we have discussed more about the effects and the intermediate formation. In next session we will discuss detailedly about aromaticity. So don't miss out the next session, because you can expect at least a question from aromaticity concept. Okay, so please do more practice questions. I'll be attaching some practice questions in the description below. Please do that. Thank you.